The ancient peoples of planet Earth were very good observational astronomers. One thing that they'd worked out how to do was to compare the apparent brightness of stars in the sky. As their system developed over the years, it became known as apparent magnitude. And that's the subject for today's video. What is apparent magnitude? How can we use it to get intensity? And how can we then continue the work to get a more useful absolute magnitude for a star? Apparent magnitude can be thought of as a measure of how bright things appear to us standing on the Earth. Nice, but not hugely useful. Intensity is a measure of how much energy actually arrives per meter squared per second on the surface of the Earth. Its units are therefore watts per meter squared, and as you can imagine, is very, very small. As time went on, astronomers became more interested in making accurate comparisons between the stars. And so it became clear that a better system than "I doth declare, my lord, this is a magnitude 1 star" was needed. And so during the 19th century, the scale was redefined using strict logarithmic ideas. Here's the definition now. A magnitude 1 star has an intensity 100 times greater than a magnitude 6 star. This means as we go from magnitude 1 to 2 to 3 to 4 to 5 to 6, we are in fact going up in 5 steps. And we therefore need to know what number we raise to the power of 5 to get 100. Taking the fifth root of 100, we find that it's 2.51. And so this means, unsurprisingly, that if we raise 2.51 to the power of 5, we get 100. Well, so what? This means, in effect, that if we want to know the ratio of the intensity of two stars, I2 over I1, then, roughly speaking, it's going to be 2.51 to the difference in the apparent magnitudes of those two stars. In this example then, I2 over I1 is going to be approximately equal to the magic number, 2.51, to the power of M1 minus M2. Well, M1 is 1, M2 is 6, therefore I2 over I1 is going to be 2.51 to the power of minus 5. And if you work that out, it tells you the intensity of star 2 at the bottom divided by the intensity of star 1 at the top equals 1/100th approximately. And therefore star 1 is unsurprisingly 100 times more intense than star 2. As we've seen, the problem with apparent magnitude is that it depends on the distance, because obviously the intensity that arrives at planet Earth drops off as an inverse square law from the star. In order to solve this problem, a more refined system called absolute magnitude was developed, which only depends on the luminosity of the star. The word luminosity is used to describe the amount of energy radiated from a star. This is obviously of the form of electromagnetic radiation. For stars such as our Sun, this figure is, as you'd expect, absolutely enormous, of the order of 4 times 10 to the 26 watts. Absolute magnitude is the apparent magnitude that a star will have if we bring it to a distance of 10 parsecs from planet Earth. In other words, if you want to compare the absolute magnitude of, say, two galaxies, we imagine what their apparent magnitude would be if we brought them both to the same distance of 10 parsecs. This is great because we have effectively removed the variable of distance from our comparison of magnitude, and it enables us to make much more meaningful comparisons.